Here's our ParaView window. Let's load the result file and run the result ht5. It's called job.cfs. We have it here in our pipeline. Again, I will disable the surface regions. We have visualizations only in the volume. And the first new thing we have to consider here, we have now a multi-sequence analysis. So we have to set the analysis step to 1 to obtain the static results. So click apply to load the results. We can now look at the geometry again, surface with edges to show the mesh, for example. And now we want to plot the deformed geometry. And this is done by the respective filter that's called wrap by vector. So let's apply this filter. The vector is mesh displacement. You can specify a scale factor. Let's click apply, see if something happened. No, not really. Maybe our scale factor is too small. So let's use the auto scale button, click apply, and we get the deformed geometry. Could also plot the undeformed geometry. Maybe we want to change the opacity here. You can use the search field to find certain properties. Let's make it a little bit transparent so you can see how the deformed geometry looks like. As usual, you can select this filter property and, for example, display the stress values. Now you have to specify the component that you want to look at. So let's look at the XX component, which will be the normal stress. And as you can see, we have the expected bending stress, which is maximum at the top and bottom of our cantilever. You can again use the analytical solution to check the values of the stress. Note that the stress is output at the centers of the elements by CFS++. Okay, so this was the deformed geometry. Let's head over to the next analysis type. So the second step was the eigenfrequency solution. So we have to specify the sequence step 2, hit apply again, and you see that suddenly our deformation is gone. You also see in the time bar here, we have a certain frequency steps. So these are our natural modes. Now let's look at them. The values here are the natural frequencies you recognize from the terminal output. So the first is at 18 Hertz. And what we also have to note that the eigenvalue analysis gives us complex valued data. So they are given in amplitude and phase by default. You can switch this by choosing the complex mode here. Let's choose real imaginary, hit apply again, and we'll see that the data now is called real and imag. So let's show the deformed geometry. We have to specify the vectors we want to wrap by. Let's take the real part because the eigenvalues are real valued here. And we have the first deflection mode. Let's also not color it by the stress, but by the real value. You can see the deflection. And now if we use different time steps, so for example, the second step, we can recognize the second deformation mode. We can use these navigation buttons to look at the Y direction. So here we should see, I have to actually look at 3D. So this is bending around the Y axis. whereas the first mode was bending around the x-axis. You can actually use also here these navigation buttons to toggle through time or frequency steps. So let's toggle through the modes, and we will see that now for the third mode we get the second bending mode, and so forth. Here is the second bending mode around the z-axis. Here is the third bending mode around the y-axis. Let's see if we find the torsion mode. Yeah, here's the first torsion mode at roughly 400 Hertz, mode number 5. Let's simply cycle through and we get the different mode shapes. Here is the first extension of the mode in mode 8 at 850 Hertz. So finally, mode 9, this is the last mode we computed because we have requested 10 modes in total. Okay, so let's now load the harmonic analysis. This would be sequence step 3. So let's use the slider here and load the result. The next thing I want to show you is to animate complex valued results. And here the reader plugin has a special feature here, so we can tick this box. We have to specify a frequency step. So let's take frequency step 7, for example, and look again at the deflection. So now we have 2 new fields in the data applying. This is amplitude and mode, whereas amplitude remains constant in time. This is the oscillation amplitude, and mode is the time animated results. Again, let's use the auto scale, click apply. We have the animation here. Maybe we want to color it by the stress. Again, mode for the animated result. Magnitude here for stress is of course not appropriate. ParaView simply takes the sum of all the components. We want to look at the x component. Let's rotate this a little bit and see what the animation will give us. So let's click play. So ParaView animates this over one period. You can click the repeat button here. Then ParaView will repeat the animation over time. And you can, for example, look at the animation view to get a little bit the smoother animation. You maybe want to use 24 frames. So then it's a bit slower and a bit smoother with more time points in between. So this is how you animate complex valued results. If you want to have the result animated at a different frequency step, we will have to change the frequency. So let's change it to the last frequency step here and see again the animation. And you see at this frequency, the beam oscillates in a shape close to a different mode shape. You can actually export the animation here. So if you say File, Save Animation, then it will either export a series of PNG images, or you can specify a video export. So let's call it beam F14 for the 14th frequency step. And it gives you a window to choose the video properties. You can simply click OK for the default. Usually it adjusts the resolution a little bit. The resolution is determined by the size of the viewport and your screen resolution. And it will save a video file, which you can then later play. Okay, so the last thing we wanted to look at was transient results. So this would be in analysis step 4. We have to disable animate harmonic model results since we don't have complex valued results. So click apply again. We have now transient results. And again, we can simply animate this in time. Since we have only real valued results here, we have to change our data again. Let's see if our scale factor is correct. Probably not. So let's auto scale this down a little bit and see again, we'll plot the stress as the real valued quantity x component. Let's monitor over time what happens with our loading. And again, it's not very smooth, but you can see the beam responds to the loading and deforms downwards due to the pressure. And there is a slight oscillation here around the equilibrium position developing. And this oscillation should slowly decay and the beam come to a rest.